So, we are going to talk about line surface and volume integrals, means line integrals, surface integrals and volume integrals. Please be sure that this part is of tremendous importance in the physical sciences and tremendous importance in the engineering sciences. You just cannot do without what we are now discussing. So, essentially we are going to stick to what is a 3-dimensional space. We have been only talking about 2-dimensional spaces or essentially function of 2 variables. So, but if you look at the place we live in, we always are aware of length, breadth and height. So, basically we are aware of 3 numbers, length, breadth and height. So, basically in a 3-dimensional space, any number, any point can be expressed by its length, breadth and height, which is called the coordinate of the point, and it is given by 3 real numbers, say x, y and z. And so, this is the x axis, the y axis and the z axis. So, if I connect it with the origin O, of course, we have to fix our axis, coordinate axis, the reference frame with some origin O, which can be arbitrarily chosen, and this distance is computed just by using Pythagoras theorem. And just like in the 2-dimensional case, the distance from 0 is just this quantity. Now, if you look at this point x, y, z, if I have a point x, y, z here, it has one direction, if this is the origin. So, if I take the origin at some point and if I take a point here, it gives me x, y, z, and then if I take a point here, it gives me another x, y, x1, y1, z1. So, these two things have, they might be of same distance from the origin, but are different objects because they are pointing in different directions, and these objects which has both direction and magnitude is called a vector. So, this is of great importance that we note this fact. So, here along the x axis, y axis and z axis, we consider 3 vectors which are of length 1, of distance 1 from the origin. Along x axis I consider the I vector, along y axis I consider the j vector, along z axis I consider the k vector. Then any vector which I now denote as r vector, so this could be denoted as r1 vector. This r vector can be always written as in terms of the coordinates xi plus yj plus zk. Those who know some linear algebra would immediately recognize that I, j, k are nothing but the canonical basis vectors. So, but let us talk in the way physicists would actually talk about. And in this, so here we call mod r the distance vectors. Here among the vectors, I would have some important way of looking at things. There are certain important operators which I will again go to the board and do, which will be much better. For example, if I take function of some r vector, it could be say some function of x into I vector, some function of or maybe x, y, z, does not matter, x, y, z into I vector, some function phi 1 and phi 2 x, y, z of j vector. So, if you look at the vectorial part, this is nothing but a scalar composition of a vector. So, you can always write a vector in this form, because the length of this would be exactly this x square plus y square plus z square root. So, many of you possibly know this way of writing, for many of you have studied physics. So, I am assuming that you have this basic knowledge that I can always write a vector in this form, that I scalar multiply the vector I with this, vector j with this and vector z with k, and then I make a vector addition, it will give me this vector, the vector r. So, I can have you can also write the thing in this particular fashion, right. Now, if I have a function of 3 variables, so these sort of functions pretty often come up. Suppose I just have a function of 3 variables. And then there is the important operation called the gradient operation, which is nothing but a vector collecting all the partial derivatives. So, this is nothing but a collection of partial derivatives, sorry, del phi. So, we will be only concerned, you can also extend it to n variables, but we will be concerned only with 3 variables. Why I am writing this? Because you are already aware of this for 2 variables, but so I am doing this to make you aware of that we can make an extension to 3 and more, but we will be just concerned with 3 here. There is a very important operation that given a vector v, right, there is an operation called this is the grad operator. Physicists also call it the nabla operator, and this is the divergence operator. How do I do it? So, just like the vector function v, it is possibly a function of x, y, z. So, if at any point in x, y, z I can have a vector function like this. Basically, this is R vector is basically x, y, z, f of x, y, z is this, then this represents a vector field. This is what is called a vector field. So, v vector is written as v1 I vector, v2 and these are scalar, v2 j vector and v3 k vector. So, the divergence operator is often written as del x, del x, del y, del z. This is usually written as divergence, means from a point, let say a light source, how the light is diverging in all directions. So, that is the physical meaning, or trying to look at a spread of a physical quantity from a given point. So, divergence actually now can be written in the following way. Basically, we are looking at the dot product of 2 vectors. Dot product is and we do the operation like this. So, this vector, so these are some quantities, these are components, these are coordinates of a vector. So, that can be also written as del x I plus del y j del z k. And this you take an inner product, dot product with this part v1 I vector, v2 j vector, v3 k vector, v1, v2, v3, all these can all be functions of x, y, z. So, finally, what you land up is you multiply, take ddx of v1, ddy of v2, ddz of v3. So, del dot v finally becomes a scalar, which is del v1 del x plus del v2 del y plus del v3 del z. Similarly, you can talk about another operation called the curl operation. So, curl operation is like putting a screw. So, basically you have 2 vectors A and B. So, basically this is the base of a screw, and you are now trying to rotate this screw. You are trying to rotate the screw from A to B in this direction. So, then the screw would actually get inside a wall. For example, there is a screw and if you want to rotate the screw here, it will get inside the wall. So, the vector, the movement of the vector is along this direction. This gives me what is called the A cross B, that is called the cross product. So, the curl operation is based on the cross product. So, it is the same operator del operator is this operator del x del z. So, physicists are always using this, theoretical physicists are always using this operator. mathematician would not like this sort of symbolisms, because this does not mean anything to a mathematician, but to a physicist it has a lot of meaning. It is a del operator, because you can play a lot of games with this. So, and you get you can get conclusions about physical things. So, it is very important. So, curl of a vector V, what does it mean? So, this is defined as follows: I j k. Again it will not make sense to mathematicians, because you are talking about a determinant and you are talking about matrices in, you are talking about basically vectors in them, I vector, j vector, k vector, del del x, del del y and del del z, but it is no harm if you think like a physicist. Now, you obviously calculate the things out. So, now if you look at this, then this vector, the v vector, I should maybe putting an arrow if I am trying to behave like a physicist, then this is what? This is nothing but I into this minus this. So, you will have I vector, or rather I should put this first, del del y of V3 minus del del z of V2, del del V3 del y minus del del z of V2, this into I vector. So, it is a vector. So, the curl operation gives a vector, grad operation of the gives a vector, only the divergence operation, sometimes written as div V, this gives you a scalar. Now, you have to take this and this. So, it becomes del x of V3 minus, it is just taking a determinant in the standard way, but it is really not taking a determinant. You can write it in the form of determinant, but this is actually the definition. It is a cyclical movement of the vectors, del V1 del z, z vector, j vector plus del x V2 minus del y V1 k vector. This is actually the definition of curl, but physicists have invented this shorthand of writing this whole thing in the standard form of a determinant, but obviously mathematicians will not really like this sort of things. Yeah, sorry. So, it is like a standard taking of a determinant. So, it is like a scalar 3 2 3 1 2 1 like this. So, once this is done, you can actually compute out these sort of things, these objects. Now, once we have these ideas in mind, you can compute out very simple examples of this. This is just too simple for me to waste time on at this moment, because we always run short of time. So, we are going to introduce what is called the line integral, and then we are going to talk about the volume integral and the surface integral and the volume integral. So, what about a line integral? So, basically line integral is nothing but you want to integrate a vector over a line in a space, say starts from a point A and this line goes to point B. So, you can break this line up into small partitioning. Integral is all about partitioning, constructing and taking this damn stuff over those small partitions and then moving on and summing up. So, this is elemental interval which I call del L, dl, it is the line element. So, basically I am looking at the integral v dot dl from point A to point B, right. So, this is what I am really trying to figure out. Now, suppose I am in a situation where I am talking about, so v dot dl. So, dl now essentially consists of what? So, this is the line element and basically this is nothing but is a piece of an arc. So, if it is x, y and z, you know how do you write the piece of that arc. So, each length is basically, this is nothing but dx square plus dy square plus dz square root. So, you take one of them out and then you keep the rest. So, we will just show you by an example how to calculate this, but if you are trying to now consider a path which is closed like this and trying to take an integral from this end to this end, if it is over a closed path, right, then you are over the closed path, you essentially are talking about line integral in this form. Then we put a circle here to say that we are moving over a closed path, but the moving over a closed path does not always give you integral 0. So, what if you look at dl vector, what is the dl vector, the length vector? Look at dl. So, what it has? It has this small length has 3 components. So, there was some x, y, z, and then you have made a little change to x plus del x, y plus del y and z plus del x. So, this was x, y, z coordinate, and then you have changed over to x plus del x, y plus del y, z plus del z, that sort of thing. So, basically when these are very small, del x is dx, del y is dy, del z is dz. So, basically you know that the differential is nothing but for the independent variables nothing but the very little change that you make of the variable. So, what does dl consist of then? dl actually is dx of I vector, dy of j vector, dz of k vector, and that is exactly v is actually v dx plus v1 dx plus v2 dy plus, so this whole thing is actually v1 dx plus v2 dy plus v3 dz, that is exactly it. So, let me just work out an example here. So, let me now consider one example. So, let v vector be given as y square I vector 2x into y plus 1. You see, it can be functions of x, y, z or just x, just y, whatever you want. So, I did not have anything say, so this is in 2 dimensions just for fast introduction. So, now I want to take, so I can put 0 into k vector. So, this is just essentially a 2 dimensional stuff, but if you look at it in 3 dimension, you can actually go in 3 dimensions also. Basically then let me talk about the 2 points that I am choosing, A and B. So, A is 1 1 0, so it is something like 1 and 1 and 0. So, this is the point 1 1 0. From here I want to go to 2 2 0, this point. So, essentially it is a 2 dimensional stuff. The vector is essentially a 2 dimensional vector, but you can look at it from a 3 dimensional perspective also, does not matter. So, B is 2 2 0. So, you see, so here I have written a to b actually means basically you have to integrate, but putting the proper limits on x and y. So, then here what would happen? Here I would have, now suppose we want to move along this bold green path. So, we want to go from 1 1 0 to 2 2 0 on this path. So, we are, instead of, I am looking at the 3 dimensional thing in this 2 dimensional picture. Now, along this, so dl is this one which we have already also written there. So, along this path I first move from x equal to 1 to x equal to 2, and I do, so I do not make any change in the levels of y and z. So, this is the first part of the path, this is the second part of the path. So, in part 1 of the path dy is 0 and dz is 0, there is no change in x and y. So, basically I have the dx part. So, basically integral v dot dl, so dx is changing from 1 to 2 is 1 to 2, so x square dl. So, v dot dl is y square dx. So, what is y here? So, y has maintained the value 1, it has not changed. You see y is in the, we are changing horizontally. So, there is no change in the y value. So, between when x is changing from 1 to 2, y remains to take the value 1. So, basically it becomes 1 to 2 dx. So, this becomes 1. Now, we go from the point, this say if I make it A, B, C, I have come now from A to B and now I have to go up to C. So, if I have to do that, let me do the calculation here on this same page, so that you do not lose the track. So, here I am changing only y, I am not changing z, I am not changing x. So, my dz is 0 and my dx is 0. So, my dl is dy z vector. So, what does this mean? What is my v dot dl? But along this path, what is the value of x? That see, you know this. So, my v dot dl, so my integral v dot dl, this will be integral, what was my second part, 2x into y plus 1. So, y is now changing from 1 to 2 into dy. But what was my x? X is held at 2. So, when y is changing from 1 to 2, my x value is 2. So, basically I will put 1 to 2, 4 into y plus 1 dy, and this will give me the value 10. So, finally, I will add these two things. So, to write that my integral a to b, a is 110, b is 220, this is 11. The question is, what will happen if I take it from point A to point C? You can try out by doing so. From point A to point C, you observe that only z does not change, but x and y both changes, right. So, basically you have to write it in this format. So, dl would be exactly the same way we have written. So, if I go from now, I want to go from on the straight path. So, from 1 1 0 to 2 2 0. So, here observe what is the important thing. The important thing to observe here that is that x is equal to y, and the second thing is to observe that dz is equal to 0. So, my integral v dl will have, so is we have to go from, basically I can put dx equal to dy here. So, in this case my v dot dl I will put y square dl is dx, dz is 0 plus the next part is 2x y plus 1, and I will put the value here as dy, but dy is equal to dx because x is equal to y. So, x is equal to y, this will become x squared dx plus same going from 1 to 2, going from 1 to 2, here I will put x 2x into x plus 1 dx. So, if you evaluate this, you will get finally the answer 10. So, the message there is that if you move from 110 to 220 along the path 1, we get the line integral to be 11, but if we move along path 2, we get the line integral to be 10. So, but there are certain cases where the line integral does not depend on the path on which you integrate, they only depend on the endpoints. That sort of vector fields where it happens is called said to be a conservative vector field, and it is of prime importance in physics. For example, gravitational field is a conservative vector field. Now, we are going to talk about surface integrals and volume integrals. So, surface integrals is that, okay, you have a surface and over which you want to do the same sort of integration. So, if you have a surface like this, then dA is a small area, the elemental area, right. So, this is the elemental area on the surface S, and the surface area, if you want to express the area as a vector, it is a vector pointing outward from the surface. This is the dA vector and this is the magnitude of the vector, this is the dA, this is the surface, the whole surface. So, of course, there is little bit of ambiguity about which way is the outer one, which way is the inner one. If the surface is like this, I can say, well, okay, I can think that way as outer one, but usually there is an understanding that, okay, for example, if the surface is a closed surface, then you can understand what is the interior and you know what is the exterior. So, anything which is pointing toward the exterior is the one, is the direction of the elemental area. So, for example, you can, we will just take an example here. So, you take an example of V vector now. I want to take it out on a cube, I want to find the integral of this on a cube, on the surface integral, a cube which is of length, breadth and height 2. So, in the next class we will first start by computing this one. Once we start by computing this one, we will then go over to volume integral, show you how to compute and mention several important theorems using these integrals, and that will be the end of the course. So, it is the same game here, you know, if you take an elemental area, you first you take one area by one surface by another, I want it over the whole surface. So, you take the 6 surfaces, so the elemental areas are like this. Suppose I want it, I do not take 6 sides, I take it over 5 sides, okay, I forget the bottom. I will take it over, say, this side, this side, this side, this side and the other side outer. So, this is how I think about the elemental area. I know what is which is the inside of this cube and what is which is the one which is for which part of the cube is the outside one. So, if I know this, I can easily draw out the, you can also take the 6th one, you can go, the outward curve would be like this, but okay, you can just do it for the 5 ones. So, try them out. So, here what is the area, an elemental area, if a small elemental area here for the very far one facing us, the very far one facing us, the elemental area is dx dy, dy dz, because essentially it is the change you are looking, the length and breadth is, length is y and the breadth is y and the length is z. So, it is dy dz into x into I vector, the I vector is here. So, it is the vector along the I vector along the x axis. So, you have to just find the elemental areas like this and just go on doing it step by step, that is all. Here you have to have a double integral, because you will have in terms of dz dy, dx dy, dz dx and all those things. So, we will just try to do the calculation very fast in the next class and go to volume integral, do a calculation and mention the theorems of Stokes, Green and Gauss, and with that we will end. We will not have time to really go through doing examples, then we need much more classes to finish it. So, we will just end it here. Thank you.